Choosing between a gas car and an electric one usually starts with a conversation about carbon footprints or fuel costs. Under the hood, however, these two machines share almost no common DNA. They move using two entirely different mechanical architectures. A traditional internal combustion engine relies on thousands of controlled explosions every single minute. It takes the thermal heat from burning fuel and physically forces metal pistons up and down to create mechanical movement. An electric vehicle removes combustion entirely. Instead, it runs electricity through a stator and rotor, using electromagnetic fields to turn electrical energy directly into kinetic movement. Workshop reliability depends on which of these systems can withstand years of daily use, regardless of what the marketing brochures claim. To find the answer, we are going to strip away the hype. We will look at the raw mechanics, track the exact energy efficiency, and review the actual service requirements of both platforms. Deciding whether to give up the gas pump requires looking past the exterior paint and understanding the radically different physical anatomies of these machines. A traditional gas-powered drivetrain requires a complex sequence of components to work. You need a fuel tank, an engine block with pistons and valves, an exhaust system, and a multi-speed gearbox. To make all of that function together, you are relying on roughly 2,000 individual moving parts. That mechanical complexity comes with a steep penalty, intense internal friction, and a massive amount of heat. This Sankey diagram illustrates what happens to the energy in a gas engine. Out of 100% of the fuel energy entering the system, a massive branch diverts downward. This represents the heat lost through the radiator and out the exhaust pipe. Only 20 to 30% of that energy actually makes it to the wheels as kinetic energy. Drivers accept this massive 70 to 80% energy waste for one highly practical reason. You can refuel the car almost anywhere in the world in about 3 minutes. The structure of an electric vehicle operates on an entirely different premise. The entire powertrain relies on a high-voltage battery pack, a motor containing a stator and rotor, and a single-speed reduction gear. Because of this design, the EV powertrain operates with roughly 20 moving parts in total. Look at the EV Sankey diagram now. Because there are no pistons creating friction and no fuel burning, the heat loss branch shrinks drastically. Up to 85 to 90% of the electrical energy flows straight through to the wheels as kinetic movement. Choosing an EV means trading mechanical complexity for a highly efficient, simplified drivetrain. You gain a mechanically reliable vehicle, but you become completely dependent on its electrical systems. The way an engine is built dictates exactly how it feels when you step on the pedal. In a gas car, you press the accelerator and wait for the engine to build up revolutions per minute to reach its peak power. The torque arrives on a delay. It builds progressively, dropping and rising again every time the transmission shifts up a gear. Electric motors don't have to spool up. There is no combustion cycle to wait for and no multi-speed gearbox to shift through. This dual-line graph comparing torque to RPM highlights the exact difference. The curved line shows the internal combustion engine gradually building torque as RPMs rise.
But look at the EV line. It starts flat at the very top. An electric motor delivers its absolute maximum torque instantly, at 0 RPM. Because of how the motor is wired, an EV also introduces a completely different way to slow down, called regenerative braking. When you lift your foot off the accelerator, the electric motor reverses its role. It instantly becomes a generator, capturing the car's forward momentum to send electrical energy back into the battery. This slows the car down without ever touching the brake pads. The physical trade-off for getting instant acceleration and reducing wear on your brakes is a learning curve. Drivers have to unlearn the traditional two-pedal driving habit and adapt to controlling the car's momentum with just one foot. There is a common marketing claim that electric vehicles require zero maintenance. The reality of a traditional gas car is highly physical. You are constantly replacing materials that break down from heat and friction: engine oil, filters, spark plugs, timing belts, and transmission fluid. The clear upside to this physical maintenance is accessibility. Those specific mechanical skills are common, meaning you can pull into almost any garage globally and find someone with a wrench who knows how to fix it. A workshop handling an EV operates differently. The physical labor of draining fluids and swapping belts is largely replaced by digital system analysis. This quadrant chart maps out standard vehicle maintenance tasks: On the top left, in the high-frequency mechanical quadrant, you see traditional gas car tasks like oil changes and belt replacements. On the bottom right, in the low-frequency digital quadrant, you see the mandatory EV services, scanning the battery state of health, checking battery management system errors, and testing the high-voltage coolant conductivity. EVs do have a distinct physical penalty. Because the battery packs make the vehicles significantly heavier, they wear through tires much faster than an equivalent gas car. However, the brake pads in that same EV will often last twice as long because the regenerative braking system handles most of the stopping friction. So EV owners are not escaping the workshop. They are trading highly accessible, frequent mechanical repairs for specialized, infrequent software diagnostics and a higher budget for tires. Deciding between a gas pump and a charging cable is an acknowledgement that you are choosing between two distinct ecosystems of ownership. For drivers who live in rural areas without access to high-voltage technicians, or those who simply prefer familiar mechanics, the traditional internal combustion engine remains the practical choice. This decision tree shows how priorities map out. Prioritizing universal repairability and a familiar mechanical feel leads straight to the traditional engine block. Conversely, following the path for 90% efficiency, instant torque, and low-frequency maintenance leads directly to the battery and motor choice. For automotive professionals, the implication is strict. Technicians who restrict their expertise to wrenches and engine oil will find themselves with fewer cars to fix in the coming decade. Whether you are buying a vehicle or servicing them for a living, recognizing the structural transition from explosions to magnets allows you to make a precise, calculated decision about your mobility.